Good evening, everyone. No, it's not on. Good evening, everyone. Is it on? Okay. Let me try it again. Oh, you're much better than me. Good evening, everyone. My name is Heidi Wu. I'm your host tonight. I am an assistant professor in the physics department of Boise State. And thank you, everybody, for joining us tonight. And we'd like to thank our donors. And First Friday Astronomy lectures are supported by audience members like you. So we would appreciate it very, very much if you could consider scan this QR code and then donate to our future talks. This evening, I'm very, very excited to be introducing Dr. Yao-Yuan from University of Utah. Dr. Mao received a bachelor's degree from National Taiwan University and a PhD degree from Stanford University. And after Stanford, he received a Langley postdoc fellowship at University of Pittsburgh. And then he received the NASA Einstein Fellowship, which is one of the most prestigious fellowships in our field. And he took it to Rutgers University. A year ago, he joined the University of Utah as an assistant professor. And I'm so glad to have such a world expert of galaxy formation in our neighborhood. So Dr. Mao is a world expert on the research of the formation for small galaxies, and they create highly accurate simulations for these small galaxies, and also had led large observations of these galaxies. And Dr. Mao has answered many important questions about dark matter and galaxy formation, and using these galaxies, and which he'll tell us about tonight. And if that's not impressive enough, Dr. Mao has played several major leadership roles in the Vera Rubin Observatory and helping shape an inclusive and equitable science community. Please join me in welcoming Dr. Mao.
Thank you, Heidi. For such an introduction that is difficult to live by. How's everyone doing tonight? Great. Yes, it is, and it's much harder than I thought it would be. Let's see. By a show of hand, how many of you heard of this term, dark matter? Great. So we're done today. Let's go and watch the. All right, so as expected, I think most of you have heard of this term, dark matter. You probably have seen this pie chart before. This pie chart shows you roughly our current understanding of the universe, that we think the universe is roughly about 25 to 30% of dark matter, about 65 to 70% of dark energy, and then about 5% of normal matter. If there's only one thing that you learn from the talk today, is that there's nothing, there's dark matter and dark energy there has nothing to do with each other, with the only exception that we don't know neither of those are, and that's why we call them dark. That, you know, the reason that they call dark matter and dark energy has nothing to do with each other. It's just that we don't know what they are. In fact, they actually act quite opposite in terms of their effect on the universe. Dark matter pulls things together, while dark energy pushes things away from each other. The terminology here is actually a little bit confusing. Calling something dark seems to suggest it's something that you can still see. A better name for dark matter should be invisible matter. It's just not something that we cannot see. It doesn't absorb light. It doesn't reflect or emit light. The term here, visible matter, the 5% part of the pie chart, is also a little bit confusing because, in fact, most of the visible matter we still can't see either. There's only a tiny fraction of visible matter that we can see. You might ask, how does that distinguish the rest of the invisible visible matter compared to the dark matter? then we'll go into that today. So before we go into this business of dark matter, let's talk about this. Maybe a better term is ordinary matter. So ordinary matter is the matter that made out of all of us, atoms, elements in the periodic table, stars, galaxies. Most of the ordinary matter in the universe, however, are not visible. That exists as gas, mostly hydrogen gas. They are so cold, so you cannot actually see them. You only see things that are hot and energetic in the universe. About 1% out of the 5%, so I guess about 20% of the ordinary matter is something that you actually see. There are stars, galaxies, they emit lights. You can see that from a telescope. The rest of it, though, is invisible. Dark matter, on the other hand, not only is invisible, it also doesn't interact with all of those things. It interacts through gravity only. It doesn't have any other interaction with the ordinary matter. So how do we know dark matter exists? So I will start with this quote. I love this quote. The visibility of countless stars is no argument against the invisibility of countless others. This quote is in a letter from Friedrich Bessel when they were discussing about binary star systems. So binary star systems are systems with two stars, two suns, but usually they don't have equal brightness. A lot of the time, one of them are much brighter than the other. So that means if the telescope is not large enough, sometimes you only see one of the binary stars, right? Because it's brighter than the other one. So how did I find there are binary star systems? Well, that is because these two stars orbit around each other. So even though this one is fainter and you cannot see them, because they're orbiting with each other, the brighter one wobbles. So they see the wobbling of the bright star, and they're asking why does the star wobble, right? And so this is the quote when they were discussing this effect. And then Friedrich Bessel proposed that maybe there is invisible star, which is not really invisible, it's just that too faint to be seen, that is causing the wobbling of the other star. Now, I seem to be drift too far away from dark matter, but you will soon see that this argument about one invisible object is pulling the other object that you can see is actually how we discover the existence of dark matter. So let me just show you some beautiful picture of galaxies. These are all spiral galaxies. Some of these are, you can see the spiral because they're face-on, and some of these are edge-on galaxies. The existence of actually this galaxy, beautiful galaxy, usually, you see on the postcards or people's laptop wallpapers, actually has something to do with dark matter. Dark matter is actually what makes it stable so that they can have this really, really thin disk. But I'm going to take you to talk about the rotation of the star in these galaxies. So don't worry about it. This is not a math class. We will not be talking a lot of equations. But I want to say, the reason that we can infer mass of the binary star system is really by the motion of the star. And so one important concept that I want to introduce to you is that from mechanics, we can infer mass from motion. And the idea is that, if you are rotating something, you have a rope, and then you just rotate it. The faster you move it, the stronger the tension you feel, right? And so that is basically the same thing that we are talking about here. Instead of a rope, the pull is through gravitational pull. And so the faster the second object moves, that tells you the stronger the pull is, and hence the higher the mass is at the center, okay? If you happen to be a high school student or college student, you might want to read what the equation is about, but otherwise just know that the faster the things that are moving around the other thing, it says that the things at the center has a higher mass. So now, coming back to this galaxy, we can then try to measure the velocity of the stars around the galaxy, okay? And then just plot the velocity as a function of the distance. So this is actually a real measurement from Vera Rubin from 1978 of multiple galaxies and just plotting the rotational velocity as a function of the distance to the center of the galaxy. Now, as I just told you, if you know the velocity, you can infer the mass, right? And then you have a velocity function of distance, which means that you should be able to infer the mass as a function of distance. So how do we calculate this? Well, you also have the light from the galaxies. And you can make a simple assumption that roughly speaking, the brighter the galaxy looks like, the more massive it should be around that region. Well, it makes sense, right? The brighter it is means that there should be more stars. And if there are more stars, well, it will be more massive. And so you can infer the mass from the light. This is a visible mass. And the mass distribution will roughly look like this. Very, very high mass or very, very bright at the center, and then decrease quite quickly as it moves forward. So then if you use the equation I showed you earlier, and then move this mass into that equation, and then calculate what the velocity distribution should look like, it will look like this. So this is the predicted velocity as a function of distance from visible matter, mostly just this disk that you are seeing here. If I now compare with what Vera Rubin has measured, then we see that the velocity doesn't really decrease as fast as we predicted. Most of the measured velocity rotation curve, this is called rotation curve, by the way, kind of goes up and then, stay flat-ish. So that means the velocity we see is larger than what we predicted from visible mass. And remember, I just told you the faster velocity is, the higher the mass it needs to be at the center. So the difference of this observed velocity and predicted velocity says that there should be some other mass that does not come from the visible matter. And that is what we call dark matter. That is a picture of dark matter halo that I'll go into in a bit. But this missing matter that is inferred from the velocity is basically what we call dark matter. Okay? That is obviously not the only evidence we have on why dark matter exists. So moving to a very different type of galaxy. So you are looking at galaxy clusters. So these are not, those beautiful spiral galaxies. These are little red elliptical galaxies. They are little actually just because they look little. They are not actually small at all. These are, most massive objects in the universe. So you are looking at the Coma cluster, and all these galaxies, they are moving around of those larger galaxies. They are not really orbiting, so they are not doesn't have a very regular motion. They are just moving around. But even though they are just moving around, the velocity, the speed of this galaxy still tell you something about the mass. And there is a measurement that we can do. It's called velocity dispersion. It's by asking, looking at all this random motion of either stars or galaxies, then you can infer how much mass in total there should be in those systems. And if you, again, measure the velocity and calculate velocity dispersion, infer this we call dynamical mass, right? Because it's mass coming from velocity measurement. Compare with the mass coming from visible light. Again, you can take all the lights, convert that to mass. You'll realize that the dynamical mass is order of magnitude larger than the visible mass. And again, there's something seems to be missing between what you infer from velocity to what you can see. And that is something that we, again, call dark matter. Now, galaxy clusters actually have another really useful things for us to see the extra mass from besides the velocity. So now I'm moving away from velocities. I want you to pay attention. So this is another galaxy cluster. I want you to pay attention to this arc-like structure that you kind of see. This is an effect called gravitational lensing. So gravitational lensing is when light passing through something really, really massive. The space is so curved due to the mass in that region, then light also bends around that massive object. So here is an illustration of it. So you have some galaxies, and it's really massive. And when you have a very massive object in your universe, general relativity to us, the space also curve around those objects. And the light will follow the curved space, and hence it will bend. And it's called gravitational lensing because it actually works like a lens. So when you see from Earth, you will see the same object appear multiple times as arcs around the massive object. Now, by studying the arc and where the arc is, you can also, again, infer the mass that is causing the amount of curve by studying where the curve, the arc that you see from the gravitational lensing effect. So then you can, again, infer the mass, compare that to the visible mass, and it turns out the mass you infer from the light, the gravitational lensing effect, again, is higher. It's more consistent with the velocity mass that you measure, but much higher than the mass from the visible light. So all this evidence is pointing to there must be something that I'm missing. There must be some mass that we cannot see in the universe. So what is it? What is dark matter? So we know that it cannot be any of the visible matter. But beyond that, we don't really have ideas. Well, I should say we have a lot of ideas, but we don't know which idea is true. Theorists has proposed many, many possible candidates for dark matter, but so far we haven't really found the answer as to which one of those is. Now, that being said, it's not that we don't know about anything of dark matter. I just told you that dark matter cannot be anything that we know of. And the reason is that we know dark matter does not interact things either through electromagnetism, weak force, or strong force. So dark matter only interacts things with gravity. You might say, well, why do you have this curves that look different from the other one? Like, are you just not making the slide right? Well, there is debate about whether there's weak interaction between dark matter and and the ordinary matter, but it's like not yet confirmed. So far we haven't detected any interaction between dark matter and ordinary matter. And because of this, that is how we know that the dark matter cannot be all those invisible normal matter. Because even though the invisible normal matter is invisible, they still interact with light. We actually know there are invisible gas through absorption. When light passing through hydrogen gas, some of light will be absorbed. And then so we can see those absorption. Dark matter, on the other hand, it doesn't absorb light at all. It doesn't reflect, it doesn't emit. It doesn't have any interaction with photons whatsoever. And so that's how it was distinguished from ordinary invisible matter. So you might say, well, how can we find dark matter? Are there ways that we can identify those things? We have been trying very, very hard, but so far we haven't found it yet. Now, there are three major, I would say, particle experiments that are designed to find dark matter. And even though this looks like a cartoon, it's actually very precise in terms of illustrating these three methods. This one is called direct detection. The idea is you put a detector deeply underground. Most of the normal matter that interact with other normal matter. So if you have any ordinary particle, it will be stopped by the Earth. Dark matter, on the other hand, as I just told you, it doesn't interact with anything, right? So you are just passing through. Well, then why does it just also passing through a detector, since it doesn't interact with anything? Well, yes, it will most of the time passing through a detector, just like as if it's not there. The idea is that if dark matter has a tiny, tiny interaction with ordinary matter, then maybe as time goes on, we will be able to detect a dark matter in that detector. Okay, but so far we haven't. We also try to do this called indirect detection. So the idea is that dark matter may not interact with normal matter, but maybe they interact with themselves. And when two dark matter particles interact with themselves, there's some chance they might annihilate with each other and then become gamma ray photons. And so we have gamma ray telescope in the space looking for regions that we think are high density of dark matter and trying to see if we are lucky that we got two particles annihilate with each other and then we see the gamma ray signal. So far, we haven't found any of such signal. Finally, we have the collider production method. So this is the inverse. Instead of waiting the dark matter to annihilate and then reveal themselves to us, we basically smash ordinary particles with each other at the Large Hadron Collider in Geneva and say, well, can we produce dark matter particle by smashing ordinary particles together? Unfortunately, so far we haven't found any such signal yet. So all of this experiments so far has not been able to produce the dark matter particle that we are wishing to find. That being said, you can purchase dark matter particle on ParticleZoom. It's about $20, I think. I have one at home. All right. I just became professor last year. So as a professor would do, we're just going to do a discussion session right now. So I just told you we know how much dark matter there is. And I also told you we have no idea what it is. So how is that possible? How can we know how much dark matter there is, but have no idea what it is? So you are all sitting in groups. That's great. I'll give you 1 minute to talk with your peers in your group. Why do you think that we know how much dark matter there is, but have no idea what it is? Okay. Anyone want to make a guess? Yes. My formula is wrong. Great guess. Anyone else? Yeah, cool. Very close. Yes. I'll get to you. So there are more dark matter than ordinary matter, actually. So if you only look at matter, dark matter is about 85%. Ordinary is about 15%. I'll get to you after this one. Right, so colliding statistics from all the things that we have talked about. That's a very interesting idea. Yeah, great. All right, so those are all like great answers, and pretty much, you pretty much get it. We know how much their dark matter is. Mostly, that statement is mostly saying like how strong the effect is. Like when I say I know how much dark matter there is, I didn't really mean I know how much dark matter particle, like how many of those particles there are. I mean I know how strong the effect of missing mass there is. So in a way, I can say, well, if there are more dark matter, then the universe will be more clumped because the pulling effect is stronger. While if there are less dark matter, the universe will be more like a void because the expansion effect from the dark energy is stronger compared to dark matter. So it's the amount of dark matter. Well, it depends on whether you think the universe is infinitely large or finite. So when I say I know how much dark matter is, I mean I know per volume how much dark matter there is. So whether or not it's finite, depending on whether you think the universe is infinitely large or not. And actually, we don't know the answer to that. So the amount of dark matter is actually by density, not by total amount, okay? So one particular way that we can study the amount of dark matter is through something called a cosmic microwave background. So, you might have seen this. This is, a brief history of the universe. The universe starting from the left, where you have the Big Bang. At some point, the universe becomes transparent to the photon, which means the photon can freely travel in the universe, and that creates something called a cosmic microwave background. And then the universe continues to expand, and you have the star forms, galaxy forms, so on and so forth. And then our present-day universe is on the far right there. The amount of fluctuation in the cosmic microwave background tells you how much expansion and pulling the two opposite forces between dark matter and dark energy there must is. And so by studying this particular pattern of the very early universe, you can actually make a very precise prediction about the expected amount of dark matter and dark energy. And again, by saying the expected amount, I just mean the relative strength of these two effects. One is gravity pulling things together. The other is making the expansion of the universe faster and faster. And so the relative strength of these two forces, dark matter and dark energy, and by using the word force, it's not really scientifically accurate, but the two effects, we can then derive the original pie chart that I showed at the very beginning of this talk, which I say, there's about 27% of dark matter, 68% of dark energy. And that is from, the study of this thing. And that is actually a super precise number. In fact, the blue points is the measurement of the fluctuation, the pattern that you just see from the previous slide. We use some math to translate that fluctuation into this blue dots. The red line that you see here is if I input that exact amount of dark matter, dark energy, and ordinary matter, and that would be a prediction of how much fluctuation there is. So you can see it's a very, very precise measurement that we can make by just this simple pie chart. We can predict what kind of pattern we will see in the cosmic microwave background. So with that dark amount of dark matter and dark energy, we can actually put this into a simulation. So you are looking actually at evolution of the universe. It doesn't look like this much because at the very beginning of the universe is very homogeneous. It's very, very uniform. But as time goes on, you can start to see high density region of the universe. So these are the dark matter. They are pulling each other together, forming deeper and deeper gravitational pull. And then more and more dark matter are being pulled into dark regions. This high density region of dark matter is interesting because they not only pull in more dark matter, they also pull in ordinary matter, right? Even though dark matter doesn't interact with ordinary matter, it does interact through gravity, which means the dark matter's mass can pull and have gravitational influence on ordinary matter. I will keep talking and then just continue to show that movie again. This ordinary matter, mostly hydrogen gas, will be pulled into this deep potential well formed by the dark matter. As time goes on, there are more and more hydrogen gas that go into that center of the potential well. The density will become so high until nuclear fusion are actually being ignited at the center of this potential well. And that is the birth of a star. Then more and more gas will be pouring, more stars will form through nuclear fusion, and then those stars become galaxies. So this is basically how we think galaxies are formed in our universe. We start with a homogeneous universe, and then dark matter start to pull each other to form potential wells. Those then pull in hydrogen gas, ordinary matter, until the density is high enough, ignite the formation of a star, and then the formation of galaxy. And then those galaxies then merge with each other to form larger and larger galaxies. And hence the title of this talk, Dark Matter, the Invisible Mass of Galaxies, because we believe the galaxies live inside those high density regions of dark matter. So this is a still picture from that previous video. The yellowish points, the bright spots, are high density region of dark matter. And as I say, those regions, those bright spots, are where we believe the galaxies will form. Star will form in those regions, and the galaxy will form. We call some of these things different names. If we have a very, very high density region that have so many high density spots, we call it galaxy cluster. That is the ones that I showed you earlier. Remember, there are so many galaxies moving around each other. Each of those galaxies that I showed you earlier in that galaxy cluster is one of these bright spots that I circled within that circle that I drew here. If it's slightly smaller, oh, by the way, this is supermassive. The things within that white circle on the galaxy cluster could go to 10 to the 14 to 10 to the 15 times of solar masses. That is 1 and then 14 or 15 zeros after the 1 times the mass of the sun. Okay? Galaxy groups, on the other hand, is slightly smaller. It's only about 10 to the 13 solar masses. So 1 and then 13 zeros. Our own Milky Way lives inside a dark matter halo that is about 10 to the 12 solar masses. Just to calibrate things, the galaxy itself, the Milky Way galaxy itself, is about a few times 10 to the 10 solar masses, which means there are about billions of stars in the Milky Way. The dark matter halo that our Milky Way lives in is about another 100 times more massive than that. That is the size, the scale of the weight. The distance scale is also very different. So that high density region, that white circle that I draw under the Milky Way size system, is about 10 to 15 times larger than the Milky Way galaxy itself. So here is the Milky Way like a galaxy that you see on the far right. The size of the disk is about, only about 100K light years or 100,000 light years. And that is, about 10 times smaller than the size of the dark matter halo that they live in. So our galaxy lives at the really, really center of the high density region of the dark matter, which makes sense, right? Because I told you it pulls the gas into the very center. It needs to be such a high density in order to ignite the nuclear fusion. So it can only happen at the very, very center when the density is super, super high. Okay, so since I'm talking about the Milky Way, and I know many of you might have, if you ever have a chance to see the Milky Way galaxy, not sure about here, like Utah, if you go to the national parks, you can really see the Milky Way in the night sky. It's really beautiful. This picture, on the other hand, is taken from the southern hemisphere because I want to show you the other two objects, the large and the small Magellan Clouds. So the large and small Magellan Clouds are satellite galaxies that are orbiting our Milky Way. They are satellite galaxies just because they are orbiting another thing. It's just like the satellite orbiting the Earth. So that's why we call it a satellite galaxy. So why is this interesting, you say? Okay, let me take this picture and now zooming out. So this is taken on Earth. You're seeing the Milky Way galaxy, the large and small Magellan Clouds. So if I zoom out a little bit, you now see, our solar system would be somewhere here. All right. If you zoom out a little bit, you can see the whole disk of the Milky Way. And then the large and small Magellanic Clouds will be somewhere outside of this screen. They are also orbiting the whole galaxy. It's not just like we are orbiting the galaxy in the sense that we are part of the galaxy. They are orbiting the galaxy as galaxy itself is like far away. Okay. If I zoom out a little bit more, you can see that quite nicely. So here, Milky Way is here. We are on one of the spiral out of the Milky Way. The large, small Magellanic Clouds are here. And in fact, there are lots of other smaller galaxies that are orbiting the Milky Way. Today, we discovered about 60 such galaxies that are orbiting the Milky Way. And that is not actually unique to the Milky Way. If we look at our neighbor, the nearest Milky Way-like galaxy in our vicinity is M31, or Andromeda galaxy. If you look at it, it also has tons of other smaller galaxies that are orbiting the Andromeda. The biggest smaller galaxy that are orbiting Andromeda is also a massive object, M33. It's like a little bit like our large Magellanic Clouds. It's like one of the brighter objects that are orbiting the Andromeda galaxy. So this pattern really repeats itself. You see a galaxy, and then you will see smaller galaxies that are orbiting the larger galaxy. And the reason that this thing repeats itself is because the dark structure of the universe that I just showed you, right? You can find, one of this high density region, and then you will see slightly lower density points, like cluster around it. If you were able to see the velocity, you actually see the orbiting of that larger structure. And that happens everywhere in the cosmos. And so because this dark structure, we actually see this satellite galaxy pattern appear anywhere in the universe, in our Milky Way, in Andromeda, and also the galaxy cluster I told you earlier. There are also a bunch of dark matter densities orbiting another higher density region of the dark matter structure. So I keep saying the high density region of dark matter region of, high density of region of dark matter. That is like really a mouthful. So as a physicist, we tend to assume everything is spherical. And so I would just use this term just for simplicity. We'll call a high density region of dark matter a dark matter halo. Don't worry about why we call it halo. It's just a term that we use to refer to a high density region. So you have a dark matter halo. At the center, you have a galaxy living there. And then you have smaller halos. Sometimes we call it subhalos, just because they are smaller. The subhalo are orbiting the larger halo. And in the subhalo, you have the satellite galaxy living there. And that is why if you cannot see the dark matter part, it just looks like satellite galaxy orbiting the central galaxy. In reality, it's really they all live inside the same larger halo. Okay. All right. So this is how, this is the home of galaxies. We see all the galaxies, including our Milky Way, the satellite around the Milky Way, and then we believe they really just live inside all these halos. In fact, not only we believe that, we even think that we know what kind of galaxy live in what kind of halos. We believe that larger galaxy will live in larger halos. Smaller galaxy will live in small halos. Well, it makes sense, right? Like, what else could it be? But it doesn't just make sense. This is actually a theory that can create a prediction, right? If I say, this is my guess, then I show you a simulation of the dark universe. I can then go in there, identify, too fast. Identify all these halos, and I can put in the galaxies. And then I can ask, would that look like a real universe or not? So this is not just a theory, it's a theory that has a specific prediction that we can study. Now, in reality, galaxy formation is such a complicated process. This is just an approximation. So this is a movie to show you a high-resolution simulation that not just having dark matter, but including all the galaxy formation processes to some limitation. But you can see, it's complicated. You are seeing the gas particle here. You can see the very bright spots of where the galaxies are forming. And then you can see they are merging. You can see, well, it's difficult to see, but you can see there are, since they are flowing out, because when star form, it's a very energetic process. It will actually kind of like explosion and move gas out. So in order to simulate this is like really expensive in terms of computational cost. And a lot of physics we need to study in order to make such a simulation. But with this simulation, you can ask, if I now go into the simulation and find those larger galaxies, do they live in larger halos? And it does agree with what our expectation is, which is larger galaxies inside this kind of simulation also live in larger halos. Well, you might still not be convinced and say, well, but this is still simulation. Maybe this simulation itself is also wrong. So how would you know that this is just not a theory? Well, you can, like I say, actually make a prediction. So you can simulate only the dark structure, and then you just paint the galaxy onto it by saying, well, I'm just going to put brighter galaxy onto the larger dark matter halo and see how it would look like, right? So you have a dark structure, you paint a galaxy onto it, and then you get a distribution of galaxy. And this is a comparison of simulation on the lower right in the red color with real galaxy distribution on the upper left, which is in blue color. And this is to show you how strikingly the pattern of galaxy looks like when we just make this simple assumption that larger galaxies live in larger halos. And then we simulate the universe by making a very simple assumption that there's dark matter, dark energy, and then we just make the universe evolve from those numbers. That is not to simplify to say that galaxy formation is easy. Galaxy formation is like extremely complex, as I just said. But if you just need to know the distribution of galaxies, it's actually a very predictable statistics from our understanding of this two major components of the universe, dark matter and dark energy. I'm going to pause awkwardly for a few seconds to see anyone have any questions. Okay. I'm not going to attempt it because I'm a guest here. Right, so the question is whether or not there are other theoretical alternatives compared to dark matter. So there is one particularly famous theory is called MOND, modified Newtonian dynamics. So MOND basically say, well, instead of Newtonian dynamics, maybe you modify at a large scale. So instead of saying there is dark matter, you just say somehow the gravity is actually stronger than we thought it would be at a larger scale. It cannot be stronger at small scale because we measure that very well in our labs on Earth. But you say, well, what if the gravity is actually much stronger than you thought when you go to much, much larger scale? So it does explain many of the phenomena that we can see. But today, there are specific things that we have observed that is very difficult to be explained by MOND. That is not to say it's actually completely ruled out. There are still people, studying whether it's really like MOND would be more likely theory compared to dark matter. At the end of the day, when I say dark matter exists, I mostly are referring to this phenomena exists, right? As I just told you, so far we have never found a dark matter particle. I still don't know what it is. But we know the phenomena exists, whether it's coming from a particle or through a different dynamics that we don't fully understand. But that's a great question. I'm going to take another one and then move on. Very interesting question. Depending on how you mean orbiting, like we talk about the binary star, the kind of orbiting. If you consider the orbiting, then Milky Way is actually kind of orbiting with Andromeda, in the sense that some of you might have heard the forecast. The Milky Way is going to collide actually with Andromeda galaxy in about, I think, 50 billion years. Make sure you mark down your calendar. It's going to be a very exciting event. Actually, it's actually not exciting at all because all the stars will be passing through each other. You will not feel the same. But Milky Way will be merging with Andromeda, and then the whole system actually will be orbiting the Virgo cluster that's nearby, and then merging with all the galaxies in that Virgo cluster. Okay, so I will take some more questions later, but now I'm going to tell you that since we haven't been able to find what dark matter is, but we have learned the existence of dark matter through all these galaxies, are there ways that we can learn more about the dark matter by observing galaxy even more closely? So, as I say, while we don't know what dark matter is, there is no lake of theories of what dark matter particle might be. This very cute illustration actually just show you a few possible things that people have proposed for dark matter. And even though it's just a cartoon, it actually shows you some of the things about whether the dark matter particle are not interacting with each other, or like interacting with each other, or like really like isolated alone. So like there are different theories of what dark matter particle might be. So the question is, are there things that we can do, right? I told you that we cannot see them from experiments that are on Earth. Are there things that's astronomical that we can try to observe in order to distinguish some of these models? And so it turns out, with different type of dark matter, it actually predict slightly different structures in the in the dark structure that I just showed you earlier. And here are 3 examples. So I know it's bright and it's difficult to see, but you can squint, and you can see that for the warm dark matter, you have much fewer the subhalo that I was talking about compared to cold dark matter. So these are 2 different types of dark matter. For self-intended dark matter, this is another type. It's even more difficult to see, but the bright spots on this one is actually less bright compared to this one. Okay, I know it's impossible for you to tell that. But this is saying that, remember, all this bright spot is the nest of galaxies. So if one dark matter is the actual dark matter particle, it will make a different prediction of the number of satellite galaxies that we were able to observe compared to if cold dark matter were the actual dark matter particle. And so by observing the number of satellite galaxies, we should be able to put constraint or like distinguish between these different types of dark matter models. Right? It's a very simple counting argument. You count more small galaxies or fewer small galaxies. And so what we can do is we can go into the Milky Way and say, well, let's count up all these galaxies, the satellite galaxy. This is satellite galaxy we have found so far. They're orbiting the Milky Way. Milky Way is at the center. And then compare to the prediction from simulation of different dark matter particle types. Different simulation will then predict different number of these small galaxies, satellite galaxies, and then we can compare that with the Milky Way, and then derive what kind of dark matter particle it should be. So that sounds simple enough. The tricky thing is that how do you know the Milky Way itself is not a spatial case? Just like all of us, some of us are taller, some of us are shorter. Like what happened, Milky Way just happened to be an outlier that they just have a little bit more satellite galaxy compared to a regular Milky Way galaxy. And so that is why it makes this business so complicated. It's because we, as astronomers, we cannot just do an experiment easily. All we can do is just by observing. We can observe only that it exists in the universe, and we are given the Milky Way. It's not like we can choose to go to another Milky Way galaxy and do the measurement. So, a lot of my own research is trying to find Milky Way-like galaxies outside of the Milky Way, so in other part of the universe, and then so that I can make a statistical statement about how unique Milky Way is. So this is a survey that I've been leading called the SAGA survey, Satellite Around Galactic Analog. So galactic analog is Milky Way-like galaxies. We go out and find Milky Way-like galaxies, and then we survey the satellite system around it so that we can compare whether Milky Way is like tend to have more satellite or fewer satellite in comparison of all these other galaxies. And the hope being that we are putting the Milky Way on a scale with all the other Milky Way-like galaxies. So then when we are comparing the Milky Way with the different documented model, we have a more fair comparison because we know where Milky Way sit compared to other Milky Way-like galaxies. Okay, I'm going to skip a few slides and show you this. Okay, so Milky Way, we talk about. I mentioned that we have found like 60 satellite-ish, and then this is Andromeda M31. So far, we found about 25 satellites. We find fewer satellites here, not because they have Andromeda have fewer satellites, just to be clear. We find fewer satellites because Andromeda is further away. So satellites that are further away means that even if they have the same intrinsic brightness, they look fainter, right? And as you all know, if something looks fainter to you, it's more difficult to discover. And that is the reason why it has fewer satellites. Not because they're intrinsically fewer satellites, just because basically the fainter satellite in the Milky Way will be too faint to be seen if you move that to a further distance. And with that concept, as you move further away out, you see fewer and fewer satellites. Not because there are fewer satellites outside of the Milky Way, but because they are further away. So you are losing the fainter side, the fainter half of the satellite population that you can see. That being said, we can still compare the bright population with the Milky Way. So this is the SAGA survey. It roughly covered this distance range from 25 to 40 megaparsec. But even though we can only see the very bright end of the satellite population, we can see a lot of the systems because we are not limited by our Milky Way. So we can now compare the Milky Way, the bright satellite population of Milky Way with all these things and see if Milky Way is particularly spatial. And it turns out Milky Way is actually not that spatial. Milky Way is roughly sitting right at the center in terms of the number of bright satellites there are in the universe. Now, what we really want to do is be able to find more and more satellites, right, the fainter half of the population, even if they are further away. And that just requires us to have better and better telescopes. So I'm just going to end this with saying that, we are having telescopes. So this is DESI, the Dark Energy Spectroscopic Instrument that is in Arizona, in Cape Peak. This is taking spectra of lots of galaxies in the universe, and we have been using it to find these small galaxies as well. And then there is another observatory called the Vera Rubin Observatory that is currently being built in Chile. This is going to be the largest CCD we have ever built in human history. And it's going to map the sky to incredible depths. By depths, I mean like how far we can see. And the idea is that with all this new current and new instrument, we will be able to map out all these small galaxies around all the Milky Way, systems, and then be able to use these systems now have a more fair comparison with the documented model that I just talked about. Because we cannot just compare one system with a different model. You cannot make a statistical conclusion from there. But by these future surveys, we will be able to survey a lot of those systems and then later, hopefully, using astronomical observation to get into what really documented is. So with that, I will thank you for your attention. Okay. Right, so mostly they are competing effect. So if there are more dark energy, there you'll see less clump because the dark energy will move things away from each other. If there's more dark matter, it will be more clump. Now you might ask, can they both be high? Well, it can because the universe also have a fixed amount of matter, well, fixed amount of energy and matter it can be. Otherwise, the universe will actually have a different geometry. You might have heard people say the universe is flat. And the universe is flat means that the total amount of energy plus matter is actually a fixed amount. So far, we have not observed any evidence the universe is not flat. And so we actually know the total amount of dark matter plus dark energy is actually a fixed value. Mm-hmm. Is that originated with outside of the universe? Okay, so the question is, how do we know the expansion is coming from just like inside the universe, not outside of the universe? We don't know. We don't know. Well, the first of all is that, do you believe there's outside of the universe? Like by definition, universe, the word universe means like everything. So there is a philosophical question about whether there's outside of the universe, right? So if you believe universe is everything, then you need to come in from within, inside. But there are definitely theories about like extra dimension and things like that. But like even in those theories, how would you say that is extra dimension not part of the universe? Is that outside of the universe? That becomes like a more like semantic question. So I guess the answer is we don't know, but it also partly define depending on how you define the universe. We'll go with first. Yeah, so there is actually a theory that a specific type of black hole might be dark matter. It's called primordial black holes. So these are black holes that form at the very, very early universe, and they are so small that they might act like dark matter particles. But we actually have limits on how much those black holes might be, and they actually cannot account for, like even if they do exist, they cannot account for all the dark matter. And the reason is that even though they are really small, they can, when they're passing through a star, we will see those effects. This is a sign effect called microlensing. And through some of this effect, we can actually put a constraint on how many of those small black holes is. As for the larger black hole, we actually know that they cannot be dark matter because they don't actually form early enough in the universe in order for that effect to be seen. Good question. So I guess yes. So if a dark matter particle is close enough to a supermassive black hole, it can consume it just like it consumes normal matter. It's just through gravity. But the effect is really, really small. Like there is not, dark matter is, even though there's a lot of dark matter, remember at the scale I told you, the dark matter is much, much larger, like the dark matter density scale is much, much larger compared to a galaxy. And the black hole is like a tiny, 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 tiny part compared even to a galaxy. So even though it will consume dark matter, the amount of dark matter being consumed by a black hole is actually not that significant. Dark matter? So, Well, so the dark matter is not at all even distributed, right? Dark matter is like clumpy and fragmentary, right? So this is the map of dark matter, like in a simulation, but and as I said, the galaxies are formed inside this high density region of dark matter. So the normal matter, there are also more normal matter in the region where there are more dark matter, right? I'm going to take one and then you. Yes. No. Well, right. So dark matter, in a way, is a fact. So, in a way, we define dark matter to be something that is like contribute to the extra gravity that we don't see. So in that sense, yes and no, right? Because in a way, we just define if there's extra gravity, then we just call that effect dark matter. Now, if one day we actually find a dark matter particle, then it will become an important question to actually confirm that the dark matter particle we found is indeed that have only gravity and very weak on any other interaction. But because we haven't found it yet, so there's not much we can say about this. Like, it's by definition that it only interact by gravity, right? Because that's how we find dark matter at the first place. So I will take you first. So the question is, does different type of dark matter particle, like I show here, can they predict morphology of galaxies? That is a great. Yeah, that's a great question. So most of the morphology of galaxy, like spiral galaxy, elliptical galaxy, is mostly dependent on the age of the galaxy. It's mostly dependent on whether they have been merging with other galaxies. If they have, it's more likely to be elliptical versus another. So it doesn't directly relate it to the dark matter types. That being said, the different dark matter type not only affects the population of the galaxy at the present day, it also affects the assembly of galaxies. So even though it cannot predict a specific galaxy morphology, it might, I say might because we don't actually have observational evidence of this, it might change, say, the ratio of galaxies of different morphologies. It might change, whether there are more older galaxies versus more younger galaxies. Yes. Yes. So yeah, I didn't go into what does it mean by cold and warm, but cold and warm dark matter actually means that assuming there's dark matter particle and they are moving at different speed. Cold dark matter moving at a slower speed, non-realistic, and warm dark matter work at the semi-realistic regime. So indeed, they have different speeds. Yeah, so the question is like whether there's some other extra energy to affect the speed of the dark matter particle. So the reason that there are different speeds, mostly actually like I say, this is assuming the dark matter are particles, and the different speed actually coming from the mass of the particle. So the very beginning of a universe, the universe is really hot, right? The Big Bang. So if your particle is not massive enough, you need to have very high speed. Like there's no way to be slow, just because the universe is really energetic. So it's not actually because there's extra energy. It's really just by the nature of the particle itself. So cold dark matter are more massive particles, so they cannot be moving so fast, even though the temperature was high in the early universe. While warm dark matter is slightly lighter, so it can move faster. If you are talking about photons and neutrinos, those are massless particles, so they are moving at the speed of light, right? So this is mostly difference of the mass property of the particle itself. Okay, last question. great question. So we let's see. We know some of it, right? We know it has to interact, through gravity. So, for those who have been following some particle physics, you need to couple with Higgs boson, which give mass to things. But it doesn't interact with, either strong force or electromagnetic force, which means it cannot be coupled to photons, which is, the things that we see every day. But it can have some coupling. And by the way, I use coupling this term as it's really a jargon. It just means whether or not it can interact with certain particle. It could couple to particles that carry weak force. So you might have heard of like W bosons, Z bosons. So those could be the things, the characteristics of this particle. So what people have been doing, right? I also showed this, cute cartoon of different type of dark matter particles. So the idea is that, we theorists will say, well, what kind of model can I create so that it satisfies all those requirements? So it couple with certain particle and doesn't couple with other particle. And then create, like, what are the other degree of freedom I can do? So I can say, do they interact with each other? Do they not interact with each other? Do they have, some of this, like, do they have a symmetry within itself? There are different types of dark matter particles inside one category, right? So there are extra degree of freedom that you can put in a theory that satisfy all those general properties. But so far, we still have like zero idea about this extra part. All right, well, I will be here and I will join the stargazing. So if you have a question, feel free to find me. Otherwise, thank you so much. Do you have anything to say?
And are we supposed to stop the recording? You take a question. Oh, okay.
So I have a question. So based on that,